Scholastic Video Book Series Artificial Neural Networks Part 1. In this lesson, we are going to look at a classification using single layer perceptron model. This is a classification problem given. The following table shows sample data obtained from two different fruits. Class 1, Class 2 is actually fruit 1, fruit 2, and weight and length 18 grams and length in centimeters for two types of fruits. Train a single layer perceptron model using the above parameters to classify the two fruits. Then, using the model parameters you have obtained, classify the fruit with weight 140 grams and length 17.9 centimeters. Let's try to understand the problem. What is given here are the weights and the lengths of the two fruits, and we take fruit 1 as belongs to class 1 C1, fruit 2 belongs to class C2. And if I take this fruit weight and length as x and y axis, we can plot them in this graph here, where the weight is x and the length is 16.8 in centimeters. So weight 121 and the length is 16.8. So we get this point here. Similarly, for the second fruit, in the same class, 114, 15.2. And the class 2, the weight 210, length 9.4, weight 195, length 18.8.1. So you can see clearly that there are two classes here. The first class is here, the second one here. So basically we can find the class boundary which can classify these two types of fruits into two classes. So our problem here is to find out the mathematical expression for this and try to find out a neural network application to classify the problem. And if there is an unknown fruit given with its weights and length unknown, we can plot that here and basically we can find it using this graph. But when you come to complex problems, we need to write a neural network problem and then solve it using training. So let's see how are we going to implement a neural network for this simple problem. Again, we can say there are two classes here. The first two belongs to class C1 and the second two fruits belongs to class C2. So basically this is how we will get at the end of the neural network classification. Okay, the artificial neural network theory is actually, we'll start with some simple notations. It's a thing that can be connected using computers, it can model the human brain. If you can model a human brain in computers, we will come up with an artificial neural network. They typically consist of many hundred of simple processing units which are wired together in a complex communication network, and each unit or node, so we have a node in this system, is a simplified model of a real neuron which fires sense of a new signal if it receives a sufficiently strong input signal from the other nodes to which it is connected. So we'll see how to visualize this one. Basically, to understand that there is a thing called node. It has some inputs, then the node will fire depending on the strength of the inputs. The strength of these connections may be varied in order for the network to perform different tasks corresponding to different patterns of node firing activity. This structure is very different from traditional computers and hence make way to intelligent machines. Anyway, this is a simple model that we have discussed just now. It has inputs and some weights called synaptic weights, and there's a summing junction and a bias and an activation function and an output. So the model consists of a set of synapses here, an adder, and activation function. So let's see how are we going to put them into a mathematical form. So this is the first mathematical form that we get for this case. Basically, this is the model. We have four inputs here. Input is xj's and times the weights wk I kj's. So multiply xj with wkj to get the input to this bias function and take the summation from j equal to 1 to m to find out the value of uk Please note there is a UK, not VK yet, because there's something called bias is there. So when you want to include the bias, so we put UK plus the bias is the input to this activation function. So basically it is VK. UK plus BK is VK, and then VK is the input to this activation function phi. So once you input VK, you get YK as the output of this function. Okay, so instead of having a bias as a separate uh, thing here, we can put this inside the summation. So you can see that instead of starting from j equal to 1, now we start from j equal to 0, go up to m. In this case, j equal to 0 means the bias. So we take care of bias inside the same function and make it more simplified. So then our phi k is equal to vk, phi k times phi. If you substitute vk in the function phi, you get yk. So the limit changes from 1 to 0. It was 1 earlier, now it is 0 because we included bias in this function. Okay, so now we have this modified neuron structure where x start from 0 to 4. Basically, this is a bias. It can be a fixed input. In this particular case, +1. So it will go into the summing junction. Earlier, it was coming directly to the summing junction. Now we have bias as an input. So it's a modified neuron structure. And we have a function here. Can you remember? We have an activation function here. It can be in different forms. In our case, we can select as a threshold function or heaviside function, which lies like this. If you give a negative input, it will stay 0. If you give a positive input, it will stay at 1. So it's like a 1 or 0 output depending on your inputs. If the inputs were negative, your output was 0, will be 0. If the inputs are positive, then you get an output of 1. This is called heaviside function. And there's another one called piecewise linear function where it has a gradient here. So up to -5 it gives 0, -5 to +5 it has a linearly varying function here, and then we have a output here. When it is positive 0.5 or greater, you get 1 as the output. And this is a bit complex function where sigmoid function, where it's can represented by the exponential here. So sigmoid functions can be varied. The shape of the function can be varied according to the value of a here. We can increase the value of a to come, it will come closer to a step function or heaviside function. So it become heaviside function when you have a larger a. Okay, let's see the single layer perceptron. The neuronal model we have just discussed is also known as a perceptron. The perceptron is the simplest form of a neural network used for the classification of patterns said to be linearly separable. So we have to make sure that our patterns are linearly separable in this particular example when you use single layer perceptron. That means you have to have two classes. In between, you should be able to draw a boundary, linearly separable boundary. If you go back again to the one that we saw earlier, it's like a linearly separable boundary. So there's a linear boundary. So if you had a class C1 somewhere here, so then if you have a class C2 somewhere here, so then you may not get a linear boundary. You may have to have a parabolic boundary or some other shape of a boundary depending on the problem. But in this particular lesson, we are only looking at classification using a linear boundary. So let's come back to the theory, and we have side functions. We have the single layer perceptron. Basically, it consists of a single neuron with adjustable synaptic weights and bias. Now we will look at the method of achieving learning in our model we have formulated. So basically, neural network is the process of learning, means that we can change the weight parameters accordingly to the inputs. So this is what we have. It's called perceptron convergence or learning algorithm. We have the input variables, input parameters, which are going from m equal to 1 to n. Basically, there are 0 to m. So because of the bias vector, so we have a bias plus m inputs, and we have a linear vector here, and we put it transpose here t. It can be a column vector. Actually, it's a column vector, but we wrote it as a row vector here. And there's a weight vector, and which is again a column vector. We make it like a row vector by putting a transpose here. And there is a bias. This bn is the bias, and w1 up to wm are the actual weights, and the response is the yn. That is, if you give xn, go through wn's, go through the summation, go through the activation function, you will get the actual response. And there is a thing called desired response. That means if the neural network is properly trained, the actual response equal to desired response. If not, we need to retrain the neural networks until you get the correct or desired response for the training samples. So we'll see how it happens anyway. So there is another parameter that we are going to use here called learning rate parameter. It's a positive constant less than unity. So let's see how are we going to use all these parameters together. And first of all, we have to initialize the weights to equal to 0. If you don't know the correct weights, basically the first step is to initialize them and then perform the following computation for time step n equal to 1 up to the number of times that you want to iterate. The activation function at time step n, activate the perceptron by applying input vector xn and desired response dn. Computation of actual response is based on compute the actual response of the perceptron by using this equation. Basically, this is the weight vector times the input vector, and then it goes through the activation called signum function. In this particular case, we are using a signum function, which is a very simple function. Again, it is very similar to this the function that we saw earlier, but a little bit of a difference there. Basically, the function that we saw earlier is called Heaviside function. When the function input is 0, it was 0. When the inputs are positive, it is positive 1. But the signum function a little bit different from sigmoid function. Also, it's a little from Heaviside function. This is a piecewise linear function, but signum function is actually a function. It is a positive one if x is greater than 0, is a negative one if it is less than 0. Earlier function was 0 and 1. Now this function goes in between negative 1 and positive 1. So that means this is my weight vector, this is the input vector, multiply them together and send it through the signum function. If this is positive, you get a positive output. If this is negative, you get a negative output. So that's our mathematical definition. And now we have a thing called adaptation. This the fourth step is the adaptation of weight vector. That means if you didn't get the desired output from the neural network, we need to retrain the weights and get the correct output. Basically what happens is that if your desired output was not equal to the output that you got at that time, there will be a value here. If both are same, there will be 0. That means weight vectors will not be changed. That means wn plus 1 will be still equal to wn. This n is actually a timestamp, not the number of neurons in the number of inputs in this case. Please note that particular confusion, because we had 1 to n neurons. Basically, we normally count it up to m, but this is actually a timestamp. That means it can go up to any number of times. It does not depend on the number of inputs. Basically, it is the time steps. Please note that difference. That means n is the time step. It is not basically the number of neurons that we have, the number of input, because number of input is the suffix here. It can go from 1 to m because we had m different inputs, but n is a timestamp. That can be timestamp 1 at instant 1, and if it is if our system is already giving correct response, that means you don't have to retrain. But if the response or the desired the actual output is not equal to desired output, we need to retrain and get a new weight vector for the second timestamp. That is why wn plus 1. So there's the training parameter there. We call it learning rate parameter. It's a positive constant which is less than unity. So if it is more than unity, it will be going to infinity. So this is to stabilize the system. And the desired output can be +1 or -1 depending on what you want to get. If it is in the correct class, if it is in the class C1, our desired input +1. If it is if we decide to get class C2, we say that our desired output should be -1. If they are not equal to -1 for class C2 input, so we need to retrain it. Then we continue the steps again from step 2 to retrain this whole system. Let's see how it's going to happen. First one is the decision boundary, that is called the hyperplane, where we have the four inputs in our case, actually 1 to m and plus the bias. And if you get this one into an equation form, these are the weight vectors that if you have two inputs like x1 and x2 and w1 and w2 plus the weight, so bias, you get a linear function like this. So we have this boundary here. We have only two different variables, two vectors, two parameters in the variable. So we have x1 and x2, then you get a linear boundary here. Is the decision boundary for the two class classification problem, because we have two classes and we have two parameters to classify for the classification. Okay, let's try to use this example using the correct initial weights and bias. That means if you know the correct initial weights and bias, we can get the output without a retraining. So let's see how. So these are the weights and bias it is given. Basically, this can be obtained by training. But say somebody has trained the network and he got the values correctly, and he tells you that you have to have the weights vectors w0 and w1 and w2 at the timestamp 0 equal to -30 and 300, and your bias should be 50 here. So this is after some training. So but in this particular question, what I show here is that with the correct initial weights and bias, how are we going to get the result, the classification. So we have this signum function and the output is there. So what we do next is we try to substitute the known parameters. We have our boundary now. We're going to draw the boundary, and these are our two classes, basically class 1 and the class 2. And when you plot the using the weights, because we saw that our hyperplane is normally defined by w1 times x1 plus w time x2 plus the bias. So it's basically a straight line equation. So you plot this straight line equation using some values. Basically what I did here is that I just took some values to plot plot this line. That means if x1 is equal to 100, what will be the value of x2? And if x1 is equal to 200, what is the value of x2 again? And we got 2 points, and then join these 2 points to obtain this straight line. So this is actually a classification boundary for this particular problem. But you should bear in mind, this is not so easy to get, because this has been obtained by some training. So we have a clear boundary here. If you have this initial hyperplane in the boundary, we can easily classify an unknown parameter, unknown object. So let's see how. So this is the known ones. What I yeah, basically we got the hyperplane, saying that the hyperplane is correct. So we have this class unknown vector, that is our unknown fruit, which is given as 140 centimeter the weight. It's 140 centimeter the weight, and the length of that fruit is given as 17.9 centimeters. So what we do here is that we send it through this neural network, which has the known weights. Basically, unknown parameters are the bias and the weight and the length, and we have the weight vector, which has been calculated for us, and we assume that it's correct. So if it is correct, that means we can classify the unknown parameter, unknown fruit. So we send the unknown fruit through our neural network and calculate the weight function, that is weight times the input x, which is unknown. We can calculate this one very easily. Just multiply each number by each number. That means 50 times 1, 140 times minus 30, 300 times 17.9. So you add them together and calculate the value, which is about 1220. Signum 1220. If you can recall back again, there's a positive number. If the signum function has a positive input, it will give a positive 1 as the output. If these values will give you a negative number, whatever the number negative, then the output should be a -1, because it's either +1 or -1 depending on your input. So input to this signum function is +1220 now, so which we calculated just now, and then we get an output of +1. That means the unknown fruit belongs to class C1. Therefore, it is a class C1 output because plus 1 means class C1. So this is actually a very simple way of classifying the unknown fruit. So we found that fruit belongs to class C1. That's a simple, very simple example where we knew the weights, but that's not the case every time. So we need to find out the unknown weights as well as initial bias bias of the system. So that means we need to train the system. So let's see an unknown initial weights and bias condition where actually in this particular case I selected only just unknown bias. So we actually the 30 and minus 30 and 300 weights are still same. This is actually the correct values, but we have a bias which is unknown initial weights. But I call it unknown initial weight because weights can change depending on the bias. Because if you don't know the correct bias, then when you retrain, the weights will get changed along with the bias. Again, the same procedure we have this boundary. Yeah, this is the interesting part of this question. So if you plot this boundary, we can clearly say that this boundary does not classify these two classes into two different classes. So basically this class boundary, the boundary line, this line is actually goes on here, making this other second fruit which belongs to class C1 out of the boundary. That means it now belongs to class C2 in this particular case. If you use this boundary as the classification boundary, that means we assume that there is a classification boundary somewhere here, which is not a correct one. So we need to train it until we get it in the middle here. So initial hyperplane does not separate the two classes. Therefore, we need to train the neural network. So that is the important part of these neural network systems. Okay, so because now we can see that it is not belongs to the correct class. So now we are going to train using the known fruits. Now we have the known fruit 121 16.8. That's the first fruit in the first class, and we have the unknown weights. Basically, we assume that these are unknown. We need to find out the correct weights. So we give the fixed input. Fixed input is 1, and our vector 121 16.8, and it goes through this weight vector again as a same as what we did previously. That means our input vector 121 16.8 transpose, and the weight vector minus 100 1230 1230 minus 30 300 transpose, and multiply these together to get a value of positive 120 180 inside the signal function. That means what is coming out from the summation is 180. So it goes through this signal function, and then if it is positive 180, the signal function output will be positive 1. So that means if you have a positive output here, it will give a positive 1. So that means our desired input is correct, because we took this as class C1, and we defined that if you get plus 1, then it should belong to class C1. So hence no need to recalculate the weights. So we stop there, and the class weights are correct. In this case, we still assume the weights are correct using the first fruit, but that's not the case. So we have to train again. We use the second fruit, and we do the same thing. We input the second fruit, and it goes through the same weight functions and calculate the output of the weight, the summation, send it through the signum, and you got a minus 1. So here is the problem now. Because we use the second fruit of class C1, use the weights. Actually, these are I told that these weights are not correct, therefore it may not give the correct answer. So actually we saw that second fruit was not in the correct class. And now when you calculate this one using this input vector, you can see what's happening, because this is the input vector which is a known fruit. That's we are bear in mind, because what we are doing is training the neural network. To train the neural network, you send this one through the weight vector, and then you calculate this input of the signal function. That's what is coming out is negative 90. This should have been positive, because we have a fruit belongs to class C1. So desired output for class C1 is plus 1. To get a plus 1 desired output, we should have a positive here. So that means we have a problem. Actually, basically, we have to retrain. Hence, we have to recalculate the weights. So what we going to do is, because class C1, the output should be plus 1, but what we got here is minus 1. Hence, we have to recalculate. So now we come to this adaptation vector business. So we have an equation where we need to find out the new weight by using the previous weight. So and the desired output was +1, but we got -1 as the desired output here, the output from the system. So therefore we have a +2 here. So basically what we have is the weight vector still there, x1 is the input vector, and the d1 is the desired output, y1 is the output that you got from the system, -1, and we assume that the training the parameter eta is equal to 0.01. It should be less than 1 anyway, so we use a very small number there. It can be any number, so you can see some trial and error to find out how we can use this one differently. So when you put n equal to 1, and then actually this is n plus 1 equal to w2, and then if you simplify this, simplification, because this is the weight vector, eta is 0.01 times d1, dn is the desired output, plus 1 minus output was -1, so the actual output is -1, so you get +2 here, times the input weight vector. This is the known fruit, 114 weight, 15.2 centimeters length, and then you simplify this this equation to get this one down here, and then finally you get w1 plus 1. Basically it's 1 is n equal to 1 plus 1 is the second iteration of this system. We got the weight vector w2 to be equal to this value. So that means we have three weights values. Instead of earlier we had 1230, 3300 minus 3300. Now we have -1229.08 for the first one, and -2.72 and 300.304. Basically the initial values has changed in order to cater for this the fruit. The boundary was not correct. Now after training we got a new boundary line. So basically because of this training system, we got a new weight vector. Now this new weight vector we add here. Earlier we had previously unknown weight vectors here. Now we have recalculated the weight vector, and now we are going to find out whether this weight vector can classify our third fruit. This third fruit belongs to the class 2 and the first fruit of class 2, and we have new weight vectors. Now we send our input which was in class 2 through our weight vector, and then calculate the output of the summation, which come to this value. So negative value, basically you can just follow through these workings here, and you get signum, negative signum value, which amounts to -1. So actually what we wanted is a -1, because this fruit belongs to class 2. So we have a correct answer here. That means we got -1. That means this is class 2 output. So we got the desired output for fruit 3. Actually this is fruit number 3. And hence no need to recalculate the weight. So therefore our new weight vector still remains as it is. So we don't have to recalculate. Okay, now go to the last fruit that we had in our table. This is the fourth fruit, which belongs to class 2 again. These are also known fruits, so that means we need to calculate this one. We send it through the weight vector here, and then we'll calculate the output of the summation, which comes to a negative value. This negative value will go into the signum function. Then signum function will give an output of -1. So this -1 output is again the desired output. So therefore we have a system that is trained to classify all four known fruits into their respective classes now. So weight vector need not to recalculate, so we stop there as the correct weight vector. Now what we need to do is to see whether we had a problem with the first fruit, that is actually the fruit that we can see whether the fruit that we calculated wrongly basically is correct now. So this is what we are going to recheck the values, but basically we can put this fruit back again and see with the new fruits as to see whether we get the correct answer. Again with this fruit we got the answer to be desired answer came class C1. We got +1 out. That means our fruit 121 16.8 is correct. And this is actually the one that we missed out was this one. This is the first one which was correct, and then we went to the second one and changed the weight. So actually this actually by right we need to check it back. Basically what we did here is that we check back with the same fruit with the different weight vectors to find out whether after changing the weights this classification, which is the first fruit actually, still classifies in the correct class. So this classification is correct. That means our after changing the fruit, the weight vectors, now still the first fruit in class C1 is classified properly. And but the second fruit was the problematic one, but we changed the weights according to that thing, and now we try it again and see whether this weight vector classifies it correctly. Yeah. So when you put these values, we can we got a positive number there. That means after multiplying the weight vector with the input vectors, we got positive one, and that positive one means that our output is correct. That means class C1. It belongs to class C1. So basically, all these four weight vectors are correct now. That means our classification boundary is correct. That means if I plot the classification boundary again, we can see that it actually nicely fits down the last fruit here, fruit 1, fruit 2, but it is here. But sometimes you might argue that it is very close to this fruit. That is because we only did the iteration once. If you do it a few more times, you can make the iteration into the center. So that's actually neural network classification. But in this particular case, we stop there and then see whether this boundary can be used to classify any new fruit. So actually we can classify our new fruit using this boundary without any trouble. So you can just substitute the values. That's the first part. Basically, this is how we can get a boundary. So now you just input the unknown fruit, which is the one that is given for the classification, and then see whether that can be classified using our our neural network, because this is the neural network after training. So now this is our fruit, which has to be classified, and which is unknown, class is unknown. We send it through this weight vectors and calculate the values of the summation, and then calculate the values of the signum function. So we can see it is like, again, you can follow the mathematics here. This is the input vector and these are the weight vectors, and multiply the input vector by the weight vectors, and then get the input of the summation here. Output of summation 117.5. I think this is something ring. It's a 256.6.56, and then you get an output of +1. There's a mistake there. So you get anyway, so you get a positive value there. So please recalculate and see whether which one is correct. So you got a number there which is positive. So positive value will give a positive one output, which is the desired. We can't say the desired output because anyways, it's obviously we can check it using our graph there, whether we have this fruit close to the class C1. But anyway, using our neural network classification, if I input this unknown fruit, it says that my unknown fruit belongs to class C1. That's interesting. So basically, if you have a fruit, if you don't know what type of a fruit is it, so you just measure its weights and measure its length and send it through our neural network and tell the neural network to find out what fruit is that. Say you have a banana and an apple. So if you know this banana is normally longer than an apple, so just by using the dimensions of the fruit, you can calculate them into their respective classes. So basically, what we found is that the unknown fruit C1 belongs to class unknown fruit. This one, 147.9, belongs to class C1. So it's quite interesting. So we can try some more unknown fruits using this model. We can classify there. Actually, once you get the classification boundary, it's basically a matter of substituting that input through this weight vector and calculate the summation, find out the value that is coming from the signal function. If it is a +1, then it belongs to class 1. If it's a -1, it belongs to class 2. So you can try with a different fruit that you think that it belongs to class C2, and then see how you get the output. So if you get a -1 as the outputs, that means your classification boundary is perfect. Okay, that's the end of this narrative book. If you want for more information about neural networks, or if you like to see other books that we publish in different areas, please drop a line or just go to our website for more information. Thank you. So you can download the PDF version of this book at this website for you to follow. And yeah, this is the website basically. We have the YouTube site. You can download this video from this YouTube website, and also you can download the PDF version of this book for your reference. So you actually can mention the ISVT number to us, and we can send it to you directly without any charge, the PDF version of the book. Thank you.